So here we'll check out part A of number 2. This is on the 2014 AB exam, and they define f of x to be this quartic function, and then they give you the horizontal line y equals 4, and they tell you that the region R is the region between those. Part A says find the volume of the solid generated when that region R is rotated about the horizontal line y equals -2. So y equals -2 would be down here somewhere. So if we were able to take this region and pull it off the screen toward us and push it back into the screen down here, bring it back to where it started, it's going to trace out some three-dimensional object. We want to find what the volume of that three-dimensional object actually is. What we do in situations like this is, rather than focusing on the whole region rotating about that line, rotate a slice. If you rotate this one vertical slice about the line y equals -2, what ends up happening is when this slice rotates, what's traced out in the air is a washer. So if you have this washer that gets traced out and you want to find the volume of this one washer, what you can go ahead and do is you can find the area of the face of the washer and then multiply by the thickness to turn that into a volume calculation. So we'll talk about the thickness of the washer first. This tiny little bit of thickness that the washer has is from this tiny little dimension from out of the coordinate plane. That's a tiny, tiny difference in x values since it's a very small horizontal dimension. So the thickness of our washer is going to be delta x. Now to find the area of the face of the washer, what we're going to have to do is we're going to have to take pi times the big radius squared minus pi times the inner radius squared, right? Find the area of the outer circle and then subtract the area of the circle that's poked out in the middle. So now we need to figure out what big R is, we need to figure out what little r is. So this will find the area of the face for us. We want to know what big R and little r are. So big R. Now think about this washer being generated. Pull this slice off the screen towards you, push it back into the screen down here, and bring it back to where it started. The big radius, and I guess I'm kind of using poor notation here. The region is called R, and I'm calling my big radius R. Those are two different R's here. So I guess that's poor notationally on my part. But the big radius is going to go from the far edge of the slice, the top of the slice, down to the axis of rotation. So this vertical dimension is going to give you the big radius, and then the little radius, the hole in the center of the washer comes about because this bottom edge of the slice does not border the axis of rotation. We have this gap there. So this would give you little r. Now this big radius has got to be specified to be positive. We need to rate it as a difference of y values since it's a vertical dimension. We want to take the bigger y value. Bigger y value is up here, the higher y value in the coordinate plane, and that's 4, minus the smaller y value. The smaller y value is y equals -2. That's the y value at the axis of rotation. So our big radius is 6. Our small radius goes from the bottom of the slice. The bottom of the slice, no matter where we draw the slice, is always on f of x. So it's going to be f of x minus -2, or f of x plus 2. And so the area, the volume of this one washer can be found approximately with this pi big R squared minus pi little r squared. That'll just be the area of the face of the washer. If we want to turn that into a volume calculation, we need to multiply by the thickness, multiply by that third dimension. Now what we want to do is we want to find the volume of the entire solid of revolution, and the volume of the solid is going to be found by adding together the volumes of an infinite number of these washers. And we can use the definite integral as a tool to add together an infinite number of things. So we're going to use the integral of this as our way to find the volume of the solid. So I'm going to simplify this a little bit as I write this down. 6 squared to give you 36. I just don't want to write out all of f of x here. You'd obviously have to do that to actually carry out this integral. And let's see, that grouping symbol is going to be important. I need my exponent between this grouping symbol and that grouping symbol, and then the delta x is going to become a dx. Last order of business before going to the calculator to get your answer, since this is a calculator problem, is to figure out what x values all possible slices are going to range between within this region. So the smallest x is going to go over to this intersection point, and the biggest x is going to range over to this intersection point. And you can find these intersections on the calculator. You can graph this function. You can graph y equals 4. And you can determine that this intersection point is at 0, 4, and that this intersection point is at 2.3, 4. That's something that you wouldn't want to waste your time doing algebraically. You'd want to use the calculator's capability to find that for you. If you toss those limits of integration on to the integral and then go to the calculator to evaluate this integral, I think I've already got mine in here. If I give it a second enter and a second time, I already have my 36 pi minus pi times, there's my f of x. I've simplified it a little bit there already too, and then I've squared that, comma variable of integration, comma lower limit of integration, comma upper limit of integration, and there's your values. That's a pretty big value. It shouldn't really scare you too much that that value is so big. We'll talk about why in just a second here. So I'm going to carry 3 digits beyond the decimal for my accuracy, and units aren't really asked for here. Nothing was really specified, but this is a volume calculation, so generically we can toss cubic units on to the end of that. That would be the volume of the solid. So why is it not a bad thing that this actually turned out to be such a big value? Well, think about how much empty space there is between the axis of rotation and the region itself. You've got a lot of area, a lot of air that you're tracing out as you carry this region towards you off the screen and rotate about this, which is so far removed from the actual region itself. You know, my graph isn't really drawn to scale very well. You know, if this is y equals 4, y equals -2 is going to be, you know, I guess about right here. So that's even more empty space than what I had up there a minute ago. And because of all that empty space that we have to count for to carry this about y equals -2, we're going to get a pretty big volume because of it.